So here's a good example to utilize the integrating factor with. This right here is what I like to call a non-exact differential equation. And to verify that, I'm going to show that partial m with respect to y is not equal to partial n with respect to x. So partial m with respect to y is 3x plus 2y. And partial n with respect to x is equal to 2x plus y. So this differential equation right here is non-exact, or it's not exact. So at this point, we can't quite yet solve this like as if it were an exact differential equation because it's not. But luckily, we have the integrating factor formulas. So the integrating factor that I will employ here will be e to the integral of 1 over n times partial m with respect to y minus partial n with respect to x dx. In evaluating that, I get in my numerator, what's partial n with respect to y, it's 3x plus y squared minus 2x plus y, and in my denominator I get x squared plus x y. And I'm really just evaluating this right here in red. In the next slide I'll integrate it all, but in evaluating this I end up with 3x minus 2x, that's x. Ooh, I made a mistake here. This y squared is supposed to be a 2y. Let me erase that. So this is 3x plus 2y. And then the 2y minus y just becomes y. So x plus y in my numerator, and in my denominator I'm going to factor out this x. I get x times x plus y. So these two terms cancel each other out, and I end up with just 1 over x. So my integrating factor will be e to the integral of 1 over x dx. So here I've got the differential equation written out with my integrating factor right here. So e to the power 1 over x dx would just be e to the power of ln x. And in integrating factors, there's no need to worry about the constant of integration. Now, with an expression like e to the power ln x, those two things cancel each other out. The e and the ln, they're inverses to one another, and so you end up with x. And so now if I multiply all of this, and I'm going to circle in red, the differential equation, all of it by x, including 0, but 0 times anything ends up being 0 anyway. After multiplying all of this by x, I get 3x squared y plus x y squared dx plus x cubed y plus x squared y dy equals 0. And if the integrating factor method works, then this differential equation right here is exact. And let's see if it is. So partial m with respect to y is 3x squared plus 2xy. And partial n with respect to x is 3x squared plus 2xy. So this differential equation is exact. So at this point, it can now be solved like as if it were an exact differential equation, because it is. So here I've got everything that's been done so far to this differential equation in taking it, figuring out an integrating factor, and multiplying it by that integrating factor to make it an exact differential equation. And the only thing that remains now is to solve it. And in my previous videos, I recommended that the first step employed in solving an exact differential equation be to integrate the more complex looking of the two multivariable functions. So in this case, this function right here that I'm circling in red, is 3x squared y plus x times y squared. It looks a little bit more complicated to integrate. So that's what I'm going to do. I'm going to integrate this with respect to x. Let me change my color here. So I have 3x squared y plus x times y squared dx. And that is equal to x cubed y plus 1/2 x squared y squared. X cubed y plus 1/2 x squared y squared. And we need not worry about the constant of integration, as it will appear on the other side of the equal sign. So after getting this x cubed y plus 1/2 x squared y squared, we end up with an arbitrary function, a single variable function of y. And as I've showed in my previous videos, the way to solve for that single variable function is to take the partial derivative of this expression of the integral, this here that's circled in red, to take the partial derivative of this with respect to y, and then subtract that from n of xy and integrate all that. That would give us the unknown constant function of y. So if I took the partial derivative, we change colors here. If I took partial derivative with respect to y of x cubed y plus 1/2 x squared y squared, I would get x cubed plus x squared y. And that's interesting because, oh, I did something wrong here. Never mind, I did nothing wrong. I was actually looking at the original differential equation before the integrating factor was multiplied out. But notice that this x cubed plus x squared y, which was the result after integrating m of xy with respect to x and then taking the partial of that with respect to y, it's the same thing that I have here, and I'll circle it in blue. It's n of xy after I multiplied it by the integrating factor x. So if I wanted to find my unknown constant function of y at this point, it would be 0, because if I took my n of xy and subtracted it from this result that I got here after taking the partial with respect to y, I'd get 0. And even if I differentiated that with respect to y, I would still have 0. So in conclusion, the final solution to this differential equation right here is x cubed y plus 1/2 x squared y squared equals C.